Hey folks, welcome back. In this video, we won't cover any new material. We'll just practice some double integration over non-rectangular regions. So remember, when we talk about integrating over a region, this is not the region of which we're taking a volume. It's sort of the footprint. It takes place in the domain, and it's determined strictly by the bounds of the double integral. So let's take a look at this first question. We'll look at this parallelogram region R, and I would like to set up an iterated integral to compute this double integral over R. So we can start by imagining that we slice this parallelogram up into vertical strips, and you see each of those vertical strips will have its bottom and its top along the same lines. The bottom will always be on this lower line. It's y equals x minus 1. We can check because of the points it goes through. And the top of each of those vertical strips will be on that top line. That's y equals x plus 1. Again, we can check just looking at the points crosses. So those are our y bounds. For any x, the y bounds are determined that way. So we'll write y equals x minus 1, y equals x plus 1 as the y bounds. And then for the x bounds, we ask, well, where do we start counting? That is, from the left, where is the first one of these vertical strips? And well, that takes place at the y-axis when x is 0. And where's the last one of these vertical strips? Well, that takes place at the right side of the parallelogram when x is equal to 2. So those are our x bounds. Vertical strips, we've got the y bounds at dy on the inside, the x bounds at dx on the outside. I'm not going to go through the actual integration. You should try this on your own, but you'll find the answer is 16/3. Next question, well, it's not really a new question. I want to do the same integral, but slicing it the other way. That is, reversing the order of integration, putting the x bounds and the dx on the inside. And well, in this case, we have to slice horizontally. And looking at the top, you can see where these horizontal slices have their right and left bounds, x bounds. Starting from the bottom, we can see that it's a little different. So specifically, these blue lines I've drawn, the left lower x bounds happen on the line y equals 1, and the right bounds happen on the line x equals 2. But these green lines I've drawn on the bottom, they have their left bound, their lower x bound at x equals 0, and their right bound at x equals y plus 1. And well, where does it switch? Where do these green lines become blue lines? This happens at the line y equals 1, is where the left and right bounds would change. That's fine. We can do it. We'll just split our region up into 2 and add together 2 integrals. So starting from the bottom, these green horizontal slices I've drawn, we said the lower or left x bound should be 0, the right x bound x equals y plus 1. And the very first one of these strips happens at y equals minus 1. The last one of these happens, remember we're splitting it, so the last one happens at y equals 1. And that's that first integral. And then we pass it off to the second integral, where now we have different x bounds, and the y bounds will go from y equals 1 up to the top of the parallelogram at y equals 3. So again, I'm not going to do the anti-differentiation here, but you should check. This should also give us 16/3 because we've computed the same thing, just in a different way. This question is not obviously an integral question. In fact, there's a typo here. This should say volume, not area. But even then, it's not obviously an integral question. In fact, you could do it geometrically if you know the formula for the volume of a pyramid with the triangular base. Actually, we could prove that rule using integration. We won't do it right here, but something to think about. But this one we will do using a double integral. Remember, a double integral is the volume underneath the surface of a graph. That is between the surface of the graph and the xy plane. And it's a signed volume, so it could potentially be negative. But in this question, we want the volume bounded between the coordinate planes. We'll see it's going to be the positive, well, kind of the positive octant, where x, y, and z are all positive. So let's start by drawing this. Even if we were to draw it in CoCalc, it might not be the most instructive. But what we'll do here is I'll draw the x, y, and z axes. And since it's a plane, if we can mark down 3 points, that gives us all the information we need to know where this plane goes. So the 3 points we'll use will be easy to find. Those will be the intercepts. So how do we find the z-intercept? Well, along the z-axis, x and y are both 0. So we'll just set those equal to 0 and see what z gives us in this plane formula. And then we can do the same for the intercepts along the x-axis and the y-axis by setting 2 out of 3 of the coordinates equal to 0. And we find these. And we can draw them onto our picture and get a pretty good idea of how this plane interacts with the axes. So we want the volume of this pyramid. And in order to find that using a double integral, well, we'll integrate over the region that is the base of the pyramid. That is this region I'm calling R. I can redraw that just considering the xy plane. I need a line in the first quadrant that hits y equals 3 and x equals 2. Well, that's this line. And we could do it either way, but since our equation's already in the form y equals, I'll do vertical strips. So we get y bounds that go from 0 up to this line, y equals minus 3 halves x plus 3. We'll have x bounds asking where the leftmost and rightmost of those vertical strips are, x equals 0 and x equals 2. But what should we put inside the integral? Well, our equation of the plane wasn't given in terms of a graph, that is a function where we could write z equals f of xy, but we can do that easily enough. We'll just solve for z. And that's the formula for this plane. And then that function, depending on xy, is what is our integrand. That will go inside there. And again, I won't do the differentiation, anti-differentiation, but you can check the answer is 6. Here we have an iterated integral. It's all ready to go. But before we integrate, I'd like to draw the region of integration. This is in the domain. So we see y is going from 0 to 1. So we can mark that off on the y-axis. And then for each of those y values between 0 and 1, we have x that's ranging from the line x equals root y, or the curve x equals root y, up to the line x equals 1. Well, x equals 1 is easy enough to draw. X equals root y. This is equivalent to the right side of y equals x squared. So easy enough, just the right side of the parabola. And we know sort of which part to fill in because, well, x is bigger than root y, but less than 1. So it's between the curved part and the line x equals 1. We can put in some of the corners there, some of their coordinates. And then to evaluate, it's already set up as an iterated integral, so we can get to work on that inside integral. But when it's time to anti-differentiate with respect to x, you might be looking at this and saying that's hard. That's actually impossible to do symbolically. So we can't do it using any of the techniques we learned in Calc 2, and there's no secret technique that we didn't teach you. You can get an answer by asking Sage or some computer program to approximate it for you. You can get as good of an estimate as you want, but there's no algebraic way to anti-differentiate this integral. Not to say that we're stuck. What we can do is reverse the order. Rather than anti-differentiating with respect to x first, we can do it with respect to y. Well, we can't just charge ahead and do that. We have to switch the order, put the dy on the inside. So rather than slicing the region horizontally, which is what's happening if dx is on the inside, let's imagine slicing it vertically. We've already drawn it. So if we slice it vertically, well, these vertical strips will go from the x-axis, y equals 0, up to this right half of the parabola, that is y equals x squared. And then where do the first and last of these vertical strips take place? Well, that's at x equals 0 and x equals 1. And this is super easy to anti-differentiate with respect to y. Remember, e to the x cubed is constant as far as y is concerned. So we can plug in our y bounds. And then we'll use u substitution. This extra x squared makes everything possible. We'll use u substitution, and we can apply the fundamental theorem of calculus one more time. And there's our answer. So we'll do some more of these in class, and I'll see you soon.